Hey everybody, Jason here again with GD&T Basics, and today's video question line. Today's topic is reporting size dimensions with a CMM, and today's question from the student is, when reporting against a plus-minus size tolerance of a hole or a shaft, what actual value do you put on the inspection report? Is it the UAME? I've had issues with CMMs reporting an average size, passing the part off as good, but then not fitting correctly. Is the concept the same when reporting against a plus-minus length tolerance? So again, for the UAME, those of you that don't know what that stands for, is the unrelated actual mating envelope. So we're going to go over quickly what rule number 1 is for those of you who have never heard of rule number 1, and then we're going to discuss the criteria that you need to report in order to reject or accept a feature of size. So let's take this example here. We're going to highlight this 0.401 and 0.400. For those of you that aren't familiar with this tolerancing method, it could be looked at as exactly the same as 0.401 plus nothing minus 1,000th, if you want to look at it that way, or 400 plus 1,000 minus nothing. This is simply limit tolerancing. So again, the main point is that we can have a size dimension shown on a drawing in various ways. It's simply giving us two limits, the upper and lower limit, or for those of you that have been through our fundamentals course, the MMC and the LMC, the maximum material condition and the least material condition. Every size dimension has an MMC and an LMC. And what rule number 1 is telling us is that we have to have perfect form when we measure at MMC. In other words, we can't allow the size and form of this feature of size to deviate beyond that envelope of 0.400. Or in other words, the UAME needs to be larger than the MMC. So we're going to go through the manual inspection of this to make sure that this is a functional part. Right out of the gate, manually, you would check any what we call local sizes. That's any 2-point check, and it must be smaller since we're internal. It needs to be smaller than 0.401. So if we check from here to here, it needs to be smaller than 0.401. It needs to be from here to here, it needs to be smaller than 0.401. Cross-sectionally looking at it as well, it needs to be smaller than 0.401. So we need to make sure that this doesn't get too large. That's what we're checking when we're checking the local sizes. But when we check the rule number 1, rule number 1 is telling us is we are also controlling the form or the bow of this. We need to make sure that we don't deviate into an envelope of perfect form at MMC, MMC being 0.400. So regardless of what happens to the size of the cylinder as well as the form of the cylinder, right, we want to make sure that the combined effect of both of those don't deviate into this perfect envelope of 0.400. In other words, if you were to pick up a pin, the pin being 0.400, the MMC pin, that pin better go all the way through this cylinder. If it doesn't, you have failed either size or form or the combination of both, right? And so if you have a pin that comes in here, it needs to be, a best fit pin needs to be at least MMC or larger, right? And then we're checking the local sizes as well to check the other side of things. So between checking the envelope like this and the local size like that, that is the two absolute minimum requirements to check a size dimension. If you just did one or the other, that's not enough. You need to understand local size as well as that envelope check. So how do we do this with CMM? We simply check the point clouds, right? And how we assess that point cloud. We will still have points all around the surface. If this is a cross section of our cylinder, we'll have points around that surface, and how we assess those point clouds is going to be very important. If we simply use a best fit cylinder on that point cloud, that is neither the MMC nor the LMC limit being checked. That is not a functional cylinder that anyone in the assembly field would care about. If you told me that anything smaller than this cylinder will be able to pass through this hole, you would be lying, because something smaller would end up interfering right here. However, if we use a maximum inscribed cylinder from the CMM, we would say that anything that is smaller than the maximum inscribed cylinder would be able to pass through this hole. And so we're guaranteeing, as long as the maximum inscribed cylinder from the point cloud is not any smaller than our MMC limit, we are digitally checking this hole like we would with a pin gauge. So we're using the maximum inscribed cylinder to check the envelope. But just like we showed you you need to check the envelope as well as local sizes. So if you only report the maximum inscribed cylinder on your CMM, you're only doing half the equation. A better inspector could come up and say, I put a bore mic down this hole and got 1.54. I'm going to reject this hole. That 1.54 is outside my size limits, even though you told me that the maximum inscribed cylinder, the size of that cylinder, is inside our size limits. You only did half the equation here. They came along and showed you the other half of the equation and got a local size that is outside the size limits, and this part would actually need to be failed. And you would see why. If we use the minimum circumscribed cylinder, it actually was larger than the LMC limit of our size dimension, and we should fail this part. So we really need to use two measurement methods, just like we did manually. We had an envelope check and a local size check. This is checking the envelope using the maximum inscribed cylinder, and this is checking the local sizes, because if this point went out this way or this point went out that way, this minimum circumscribed cylinder would also grow. And so as long as that minimum circumscribed cylinder is smaller than our LMC limit, we have checked local sizes as well. So we're going to use both those cylinders to check our feature of size. And in fact, that's exactly how the ASME Y14.45, or the Measurement Data Reporting Standard, tells us how we need to report it, right? It can either be in an attribute or variable sort of way, but we need to verify that we have met both the MMC as well as the LMC of our toleranced dimension. And so we're going to check the envelope of the MMC. That either can be a best fit pin gauge as a yes, no, it passed, or we can actually get a reportable maximum inscribed cylinder and report that value. And then we would get the largest local size, and this is an example for an external feature, so it's saying smallest local size. But in the case of a hole, it would be the largest local size that you would end up reporting. And as long as that largest local size is smaller than the LMC limit, or the largest size allowed, we have met our LMC criteria. So each size dimension on a drawing is going to have two line items on an inspection report to formally accept or reject that feature. So hopefully that helps clarify the first part of the question. The second part of the question is a rather deep one, but I'll touch on it very briefly. But the reporting against a plus minus length tolerance. So let's say we had a box here, and we have a size dimension on that box. Let's say it's 1 inch. We wouldn't actually put that on there. 1 inch plus or minus 5 thousandths on the drawing. It is exactly the same in the fact that we would make sure that if this top surface did something like this and the bottom surface did something like this, we want to make sure that any local size meets its size tolerance. And we also want to make sure that the feature in its entirety fits inside its MMC envelope. So this entire feature needs to be inside 1.005, and any local size needs to be larger than 0.995. And so we are checking it in the same way. We'd have the same number of line items for a linear dimension. And again, be very careful in 2018 is this, even if this was identified as datum A down here, size dimensions do not and will not ever use datums as origin points. This is simply a size check. This is not locating this surface from this surface. That gets very deep very quick. I see size dimensions used incorrectly all the time. They become ambiguous. So an example where we're controlling the distance between stepped surfaces. If we're trying to control the distance between this surface and this surface, 1 inch plus or minus 5 thousandths. This is illegal per the 2018 standard. We can no longer locate this surface from this surface. This is not a feature of size anymore. There aren't opposing elements, right? And so we cannot check it with the size dimensions in rule number 1. We simply have an ambiguous dimension to check here. There's a lot of ways that we can assume to check this, but again, those are all assumptions and they're not backed up by standards. So if we truly have a feature of size where there are opposing elements, then we definitely apply this sort of inspection and reporting method. So hopefully, again, that helps clarify some things for you, and thanks for tuning in.
Our goal is to be your best source for GD&T information online. It's important to us that everyone involved in engineering and manufacturing have the chance to learn and better understand GD&T on your prints. We have many free resources to help you get started on your learning journey. Subscribe to our GD&T community using the link in the description below or visit our website. Test your knowledge with our GD&T and print reading quizzes. Download helpful charts and access articles written by our training experts.